In this talk, we are going to deal with the basic parameters of an electromagnetic wave, and is to know what produces the wave. And the most basic unit we may consider is just the point charge. And this is our first drawing. Here we have just a couple of charges in exactly the same way we had before, two masses in the case of the law of gravitation. And those charges have or may have signs. They could be either positive or negative. In this case, we have two positive charges separated a certain distance. Once again, we have a vector of the kind we have just talked before, and this is the unit vector in the radial direction that joins the two centers of the charges. Now, there is a force applied on the second charge, and certainly, although it's not represented on the first one. And in this case, if you see, this is a force of repulsion. The charges, if this charge was free to move, it will be pushed away from the other one. This is not the only case we may have. Also, there could be a negative charge. And in this case, the force will just be an attraction force. In other words, the charges will be attracted to each other. And if the charge was free to move, it will just collapse towards the other charge. Both will move. In this situation, we may ask, what is the value of this force acting on the charge? And for two stationary charges, that's to say two charges that are fixed in space, they don't move, the law takes a form that is very similar to the one we wrote before for gravitation. The constant, the product of the two charges, it decays inversely with the square of the distance. It's a radial force, and the sign here has to be taken carefully, because it could go in this direction, or it could be negative if it goes in the direction that is opposite to it. And we have a constant here, and this constant is different to the one we saw before. First of all, it's quite large if you compare with the g of the gravitational constant. It has different units, and it receives different names. The first one that we may say, and for historical reasons, is the electrostatic constant. Sometimes it's also called, in honor of Coulomb, Coulomb's force. Coulomb was a Frenchman that is the one that developed this and found this law. And sometimes it's also called the electric force constant. We represent this constant in this way, but sometimes we use this other expression. And here you have a 4 pi, but I will not comment on the reasons for this number. It appears very frequently in electromagnetic expressions. And we have another parameter here, epsilon naught, that is the permittivity of space of the medium we are propagating, or we have the charges immersed in. And if it's free space, that means if there's nothing, if vacuum in between, this is really what we define and use, and it has this number. This constant is directly related to the dielectric constant and the index of refraction that we all know from optics. The index is just the square root of this number, the relative value of this number. Now, let's think for a moment what happens if we just extract the second charge. There's no charge left in there. We just have a point where the charge was before. What happens now is that we still have an interaction of some kind with this charge with the medium that is surrounding it. And if we place a charge here, that will appear a force. So we say that, in fact, there is an electric field that surrounds the charge, or if you want, the charge produces an electric field. That's the basic parameter. Everything else is the same. The charge plus q, the r vector, the unit vector, the distance to the point. And the value of this field is just the force before on the charge divided by the value of the charge. That's to say that we normalize the force to the unit charge. So the electric field is just the force on a unit of charge. And the value, once again, is this. It follows an inverse square law with the distance, it's proportional to the charge, and it's radial. It goes on the radial direction. And the units are something that you are familiar with. This is the voltage unit, volts per meter. And this is the electric field. Now, what happens if we just put a charge here in a point where there's an electric field? Then we go the other way and we say that if there is an electric field in a point and we put a charge there, then a force will be exerted on that charge. And the value of this force is just the product of the charge and the electric field. And this is the basic principle that we have to deal with. If we have a charge, it will produce an electric field. And if we have an electric field somewhere and we put a charge and there is a charge there, this charge will be feeling a force that may be forcing it to move around. And this is what is going to make possible communications in a very broad sense. Here you have just a simple example. Two charges, a positive one and a negative one, separated a certain distance. Surrounding each one of them, there is an electric field. You see the arrows here. And you see that the arrows point out of this first charge, and then they follow a certain path and end in the other charge. If you see, for the case of positive charges, those electric fields are leaving the charge, while for the negative one, they are entering into the charge. And this is just a simple plot, but tells you how the fields are generated in space when you have a charge. And I am going to show you something that we use frequently. This is just tear down of a mobile phone. And the first thing you all know is that there's a battery in the phone. You have to charge the phone very frequently, probably much more than you ever wanted to do. Why? Because this battery will pump across the circuits, and you have here some examples, some lines. You don't see the circuit, the compact circuitry that is below this plate, but all around there's going to be wires and circuits on top of those currents that will be moving from the battery. All around those circuits, we will impress the information we want to send. In other words, our voice, our data, whatever we are using. And this is the antenna. Those phones have very different number of antennas depending on the applications. There is one antenna for communication. There's maybe another one to receive GPS signals, maybe a Wi-Fi, a Bluetooth. So you have different structures of this. And they are all just metallic structures. And here we have the phone, the same phone, and the antenna. This is the antenna. Everything else is covered, and this is just the part of the phone that launches the wave, the electromagnetic wave, to the space. When the battery forces the currents across this structure, those charges move around here, and they produce fields that go deep into space. So we are producing electric and magnetic fields of the kind we commented before, and also magnetic fields we'll be talking later on. Now those fields propagate in space, and now think that this phone is just a receiving phone. What happens here? Then the electric field will really force on the charges that may move around the circuit, and will exert a force and will in some way make those charges move around the circuit. And those charges moving around the circuit will carry on impress the information the sender have put in the communication system. And all across the circuit, those charges will be moving, and this will make possible to extract the basic information. So, in short, any communication system, basically what it does is just sets a set of charges moving around the circuit, reaches the antenna, launches a wave into the space, This way reaches to the receiver, and in the receiver will set in motion also electronic charges that through the appropriate circuits could just be allowing one to recover the information. And this is the basic principle we'll be seeing in all communication systems.